Hello everyone, I'm humanHardDrive, and today I'm going to be showing you a tutorial on how to use this. This is the ArduinoLab 1.0, brought to us by hobbylab.us. What this is it is a standalone USB-based logic analyzer. It has 14 logic inputs that can be clocked up to 8 megahertz. And it also has 6 logic generator outputs. So this thing can function as both a logic analyzer and a logic generator to test and analyze various circuits. And it's a really great little device for the price. So if you don't have a logic analyzer already, highly recommend one of these. But what makes this really cool is the fact that beside it being a standalone logic analyzer and logic generator, is that it is also an Arduino compatible shield. So what you can do is take your Arduino, plug it in, and just like that, you can analyze to help you debug logic signals coming off your Arduino, just like that. You don't have to break any external wires out, you can just plug everything in and debug it. So if you're having trouble with a program or a circuit, this is a really good tool to have. So let's go ahead and look at how to make this device work.
Alright, so this is the USB Oscilloscope 2 software. This is the software that comes with the ArduinoLab, and this is where you're going to do your logic analyzing. This may seem a little daunting, but we can get through this together. Alright, the first thing I suggest you do is go into Tools, Options, and you're going to check this box saying Bus A Reverse. And what that will do is it'll reverse the A bus. Because initially A0 is connected to A7, A1 is connected to A6, A2 is connected to A5, and A3 is connected to A4. So by reversing it, that puts everything back in its proper order, and it makes more sense when you're connecting it to the Arduino, and makes more sense when you're connecting pins to it in general. Okay, so these are the two buses you have here. You've got the A bus and the B bus. The B bus does go from B0 to B7 here, but ignore that. It actually only goes from B0 to B5 on the ArduinoLab. B6 and B7 are part of a different piece of hardware. So just ignore those. Now down here are your tools. So this is your frequency selector, where you can select your sampling frequency all the way from 1 kilohertz to 8 megahertz. The generator data for the table for generator data. You've got trigger options and timing stuff, which we'll all get to in due time. And this is where all your data is going to be plugged, with time in the x-axis and data individual here. Now, the ArduinoLab device is a 3.3 volt logic device, although it is 5 volt tolerant. What does that mean? It means when you're reading something, it has to be able to trip a 3.3 volt logic signal. So the Arduino can do that, but you've got to make sure you can trip 3.3 volts of logic. And when we generate stuff, it will output 3.3 volt logic, which is enough to trip a 5 volt logic system. Make note of that, be aware of it. Okay. So let's go ahead and start by trying to debug some Arduino serial communication. So what I've got here is just a dummy piece of Arduino code. I'm going to send that out to it now. So to start with, you can click on one of these, and we're going to rename this to RX, so it lines up with the Arduino RX pin, and TX, just so that it's easier to remember than A0 and A1. Okay, so we're going to set this, if I open up the serial monitor, there we go. I'm setting it to 9600 baud. What does that mean? It means the frequency is 9600 hertz. 1 bit every 1/9600th of a 9600th of a second. So you have to be cognizant of that in your frequency selection. Generally, twice that is good. So I'm going to set this to 20 kilohertz, and down here I'm going to select A, which means analyze. Analyze means that both the A bus and the B bus are set for logic analyzing. If I set this to generate, only the A bus will be used and the B bus will be set up to generate signal, but we'll get to that later. Okay. I'm going to go ahead and hit run, So it analyzes it, and it's done. I haven't even gotten to send any data out. That's kind of sad, isn't it? Run, stop. So why is it doing that? Well, the fact is that at 20 kilohertz, it's running through all of the samples it's going to take very quickly. So quickly, in fact, that I don't have time to open up the serial monitor and punch in whatever I want to analyze. That's a problem. To get around that, what you can do is say trigger on, and I'm going to select falling edge. So what triggering does is it'll only start analyzing once this trigger condition has been met. And in this case, on the RX pin, because I know that serial communication starts with a falling edge. You can also select it for rising edge and mask. So on the RX pin, trigger on, falling edge. So if I run this again, you can see it doesn't immediately stop. Keep an eye on that. So when I type in hello world, there we go. Go away. You can see now we've got useful data. If I zoom in, zoom out, there we go. Look at this on its own. Ta-da! Lovely data. We've got ones and zeros of all varieties, all two of them. So if I want to, let's do some analyzing on this data. So, go away. So if I can drag these two markers here, the 1 marker and the 2 marker, and I can put them on either side of this pulse, and I can look at the timing for it and say, ooh, look, T1 started at 449.5 microseconds, and T2 started at 551.2 microseconds, and the length of this pulse was 101.7 microseconds. Very useful information at some point, not in this case, but it's useful to know how long a signal is, or how long a signal lasts, so you can determine the length of the signal, duty cycle, pulse width, useful stuff. Now, this, before I get to that, you can also find bit sequences in binary, hexadecimal, or decimal in either direction. To the left, or that's the right, to the right, or to the left in your data. Useful. Not what we're interested in, though, because this is a UART communication, and it would kind of be useful to know what data I just sent to the Arduino. If only there were a way to do that, short of, going through and checking all the pulses. But this is a non-clock data. So how am I supposed to know what pulse is 1 and which is a 0, and when that transition happens? And it's all very confusing. Thankfully, the USB oscilloscope software has the option to analyze such data. So if I click on the UART tab under Logic under Logic Analyzer, the receiving channel is RX, and the transmitting channel is TX, and our speed, data bit, stop bit, and parity all plugged in, because I named everything so helpfully, and I click waveform to binary. You can see that it translates the signal into 1s and 0s. Then I can see that, oh yes, 68 is an H, 65 is an E, and 6C is a L. So this must say hello world. So that's really useful, and it works for both the receiving end and the transmitting end. Useful stuff. This also works with SPI communication, I2C, and one wire. So let's take a look at some SPI communication. So I'm going to upload a different program to the Arduino. This will demonstrate SPI with a digital potentiometer, which I don't actually have hooked up, but just bear with me, you'll still be able to see the data. Now, for this, I'm going to up our analysis frequency to about 500 kilohertz, because SPI is fairly quick. And in this case, I'm going to set the rising edge to pin B2, which should be pin 10 on the Arduino, if I remember correctly. And if I run this, there we go. So now we have data. Not only do we have SPI data, it appears we have some serial UART data as well. So I can click SPI, and this is where I'm going to have to plug in new numbers. The clock in this case is B5. The receiving channel is B3. And this should be, no. Yeah, that's still B3, and this is B4. Yeah, okay. Got to get that straight in my head. And I click Analyze. There we go. Now I can see useful data. I might have gotten the receiving channel backwards. That should be B4, and that should be B3. There we go. That makes more sense. So you can see what the device I'm transmitting to is sending back. it's not sending anything because I don't have the device hooked up, but you can see what the Arduino is trying to send out. So this is really useful if you need to analyze, say, this. This was very helpful to me when I was writing this code. And I could set the clock rate, the polarity of the clock, more stuff about the clock, and the data order. Really useful if you need to analyze complex signals where if you have an Arduino, the serial monitor on its own will not do. Another thing is I2C. This is really useful for I2C. I should point out, though, that I2C on the Arduino Uno is mapped to pins A4 and A5, which the ArduinoLab isn't hooked up to, so you'll have to move those 2 pins to another 2. It's not that big a deal, but you should know that that's how you're going to have to do it. Okay, so that's logic analyzing. Let's talk about logic generation. There are a couple ways you can do this. The first thing you're going to have to do is set this to generate mode. It's the G. I'm going to turn off the trigger for a moment. Now the first thing you can do is if I go under Tools and Options, I can see channel for external clocking bus B is B0. So if I come down here and I say frequency, I can set the external frequency from 1 to 1000 kilohertz. And that will make B0 generate a signal at a certain frequency. That's the first thing you can do. The next thing you can do is go away. Is I can... Wow, that's weird. So I can draw... There we go. I can draw signals. If I left click, it adds, and if I right click, it subtracts away the signal. So I can use this to draw custom waves. And let's get rid of that for a second. And then, okay, so I have to deal with that. Okay, no biggie. So I can draw custom waves. So if I drew a really, let's up the frequency ever so slightly. Yeah, 50's fine. Zoom out a bit. So I can draw something on B0. And I'm going to disconnect the ArduinoLab from the Arduino and connect pin A0 to B0 so that you can see the output. And if I run this, when I click run, it will run through one step of the generated frequency. It will still analyze on the, I'll set this back to A.0 and A.1. It will still show me what was happening on bus A. So if I click run, there we go. As you can see, the data that was sent out is being received by this, the A bus. So you can draw specific waveforms for the analysis if you need to send something dummy signals to see how it would react. This is a good way. What you can also do is if I take this UART again and I change this to, say, B0 and B1, and I clear this out. 0. Oh, whoops! I'm just hitting enter a bunch of times. There we go. So I can send specific data. So I can say 10, 12, F, A, C, 25, FC again, FF, just a couple more FFs because I need to fill out some space. There we go. Then what I can do is I can say click ones and zeros to waveform, and what it should do, like so, is draw it out. Now, for some reason, there we go. So now it's taken those ones and bring this back, ones and zeros I've had sent out, and at the proper speed with the proper data bits, stop bits, and parity, calculated it all out, and it's drawn it. So what I can do is I can then take that, set this to the falling edge again for A0. I'm going to now connect this to B1. I'm using this as a standalone logic system now. I hit run, and there we go. Now you can see what it was. And if you felt so inclined, you could go into UART, this back up. There we go. Set this to A0 and A1. Click this again. And I can see what I sent, even though I already know what I sent because it's down here. But there you go. And this works for SPI and I2C. So this really is an all-in-one package. It's really great. So if you don't have a logic analyzer already, I highly recommend one of these because it's cheap, it's really useful, and you really don't appreciate how much you need one until you have one. It's a really great tool. It's like a multimeter. I didn't have a multimeter for I don't know how long, and when I got one, it was just absolutely, you don't know how much you need this until you have it. So, really great tool. I think $40. Definitely check this out.